Let's go over the concept of center of mass. It's an important concept that we use in biomechanics, that we often want to track the center of mass position versus time and see how the center of mass location is changing during some type of movement. And so it's an easy concept to get, but it's good to just go through some of the details of it and then also go through some simple examples of how to determine the center of mass. All right, so let's do center of mass. Now, we're going to define this as the point where all mass seems to be concentrated. So I'm going to abbreviate it COM, center of mass, and it's the point in an object where all mass seems to be concentrated. And in is a funny word. I could actually said of an object because it doesn't actually have to be located inside the object. So a term that is closely associated with this and used interchangeably is center of gravity. Oh, I should have defined it first. Center of gravity. Now, you might look up in some textbooks and they may actually try to distinguish between these 2 points or these two phrases, center of gravity and center of mass. However, they are in essence the same point. And I'll go through an example of where they may not be the same point, but for all practical purposes, they are synonymous. They mean the same exact thing. Center of gravity is simply the point in an object, and again, I could say of an object, where all weight seems to be concentrated. So the only term concentrated, I will spell here, the only term that I changed is mass and weight. Weight is a force, it's a vector. And so sometimes you may actually see a textbook or a reference saying center of gravity is from regard to the vertical direction only, and that's just not correct. Center of mass and center of gravity, in essence, mean the same thing, other than this word right here. This is a scalar, and mass of an object is the same no matter where, how much force of gravity is acting on the object. The mass of an object of 20 kilograms, it's going to be 20 kilograms on Earth, on the moon, on Saturn, wherever we go in space. Weight is a force, and that is a function of the mass of the two objects and how far apart those two masses are. All right. So this is a force, this is a vector, it's represented by magnitude and direction. This is a scalar represented by magnitude only. And as I said, these are important concepts to understand, and I'll emphasize that they mean the same thing by drawing a situation where it's really probably the only situation I can come up with where these 2 points are different. All right, so I've got an object here, and maybe you can start guessing what the object is as I start drawing it out, which I'm terrible at this drawing, but let me see if I can, oh, let's see. Yeah, okay, well, hopefully you can start to make sense of this. This would be North America. This would be South America. That's Florida. I guess I left Texas out there. Canada up here, and so forth. All right, why did I draw the Earth? Well, if I draw an object on this and I draw it super, super, super tall, maybe I do some type of structure like that. Well, we know the force of gravity is a function of how the two masses are attracting each other. And if I just consider a mass here at this elevation or this far from this inner center of the Earth versus this mass up here, you can see that they're really far apart. The force of gravity would be acting greater here here versus here. Why? Because this mass is further away from the center of the Earth. And we know that the force of gravity is equal to this constant times mass 1 times mass 2 divided by the square between the distances between those two masses, or the distance between those two masses. That's an arrow. So this mass, even if it was 20 kilograms, would weigh less than this mass, even if this is 20 kilograms. And so the center of mass, if this was uniformly distributed, would be somewhere like here. And the center of gravity, where all weight seems to be concentrated, even if this were the same mass down here as up here, this weight would be greater because the force of gravity would be greater for this. So I'll put an X there and I'll say center of gravity. So seriously, a contrived example of where these 2 points are not the same. So for our class, center of mass is the same as center of gravity. And frankly, I sometimes say center of mass and sometimes I say center of gravity. They mean the exact same thing, unless the force of gravity is acting a different amount on different parts of the object. Okay? So center of mass, center of gravity, the same exact thing. All right, let's continue. And let me draw an object, and I'll draw an odd-shaped object first. And the center of mass, or center of gravity, will be the point where all that mass seems to be concentrated. And in our I gotta be careful and write and not talk at the same time. And its center mass is, we'll determine that in another video actually, but that center of mass is where if we do our kinetic analysis, and if you do this in a physics class, you may actually only concern yourself with the center of mass of the object as opposed to drawing the whole object. And this is where I would start placing force vectors acting on the object. For example, if I do the force due to gravity, I would draw a single vector acting at that point to represent the weight of the entire object. All right. So it's a nice concept to sort of simplify our drawing. So instead of drawing something complicated like that object and try to reproduce it, I could simply do this. I could do center of mass of the object, and I would start drawing force vectors being applied to that center of mass. All right, so it's important to know that that center of mass does not actually have to be a physical location in an object, and it doesn't even need to be the same point of an object if the object can change shape. So I'll do a person, for example, in maybe doing some somersaults in a pike position. This is a person's hands here, and this is the hip, this would be the knee, and so forth. I'm not that great at drawing, but let's say that this person is doing some aerial maneuver, doing some type of somersault in the air. Well, the center of mass will be a point where all mass seems to be concentrated. It's a balance point of the object because all the weight of the object will all be concentrated at that point. And so here I can draw that object even outside of the body. And this would be a balance point. This would be where all this mass, all this weight seems to be concentrated. And it doesn't need to be the same point, nor does it need to be on the object. So if the person changes position, and is now doing something like this, maybe the center of mass moves over here. It's the point where all mass seems to be concentrated. It's not a singular point. It's not a point on the body. It doesn't have to be a point in the object. It can be outside of the object, okay? Does not need to be to be on the object and not a fixed point when the object can change shape. I'll add that, when the object can change shape. Okay, all right, let's keep going on this. So I use this phrase, it's the balance point. And this is sometimes the easiest way to think about center of mass, center of gravity, is that if I put an object, now I'll draw a baseball bat. I always like a baseball bat because it has some obvious changes in distribution of mass. And if we want to find the center of mass of this object, one way that we can find a clue into where the object is we could start trying to balance the object under some fulcrum. And if you look at this object and you think that there's more mass out here than over here, maybe I put that balance point right here. All right, a fulcrum. That's close enough, but. And let's, as long as that object balances and it does not rotate this way or this way, then my center mass is going to be right above that fulcrum. If, let me try to redraw it again, the same object, roughly same object. Oh, that's not very good. If I put that fulcrum over here, and my center mass seems more drawn out here, yeah, it's not very good. It's logical this object is going to rotate in this direction around that axis. Why? Because there's going to be more mass on this side of that fulcrum than on this side. Why? Because this center mass represents a point where all mass seems to be concentrated. That means the same amount of mass is on this side as on this side of the bat. This would indicate that there'd be more mass. It has all this mass plus this mass and just a little bit of mass over here. So logically, this is going to rotate down in that direction. All right, so another way to think about center of mass is it's the point where sum of torques, which equals I alpha, is 0 Newton meters, as long as we are dealing with an initial velocity of 0, and I'll use radians per second. I could put degrees per second here, it doesn't matter. As long as the initial angular velocity when I put this object on this fulcrum is 0. Why? Because we know angular acceleration tells us rate of change of angular velocity. And a 0 angular acceleration does not mean no movement. It simply means that velocity is constant. So I want velocity to be constant and 0 when I have the fulcrum right under the center of mass. As long as I release this with initial angular velocity of 0 radians per second, it will continue to be 0 because the sum of the torques about that axis of rotation is going to be 0. That means the same amount of mass is over here as over here. The same amount of weight is on this side as this side. The same torque will be generated in this direction as this direction, and those torques will cancel each other. And the object will stay balanced with the center mass directly over the fulcrum. If I have more weight to one side of this fulcrum, this rotating point, then I'm going to have more torque acting in this direction than in this direction, and I'm going to have some rotation in that direction. I can do this one more time, and instead of the bat, I can do an example where I put a mass here. Keep doing I. A mass here, and a bigger mass out here. And I connect these with some rod, and we won't concern ourselves with the mass of the rod. Well, if you had to figure out where to balance this object, where would you put that fulcrum? Would you put it here? Would you put it over here? Would you put it here? Would you put it here? You can sometimes conceptualize where would you put it, and what you're doing in your mind is you're actually thinking, oh, well, there's more mass out here than over here. That means that to balance this, I'm going to have to be somewhere over in this region. Now we can actually figure that out. How do we figure that out? Well, we actually will go ahead and put our fulcrum right here. We can figure it out experimentally, just like I could try to balance my pen. If I try to balance my pen, experimentally, I can find where that center mass is located so that half the mass is on one side of that point and half the mass is on the other side. You can see it's not necessarily in the middle. I didn't actually get it right. All right, so now what do we do for torques? Well, remember T equals FD perpendicular. And now I've got a mass here. I've got some force acting right here. I've got some force acting right here. And I've got some force acting back here. And that force is going to be equal to the force of gravity of mass 3. So I'm going to just write weight of 3, weight of 2, and weight of 1. All right. Okay, now let's look at our next equation for torque. Sum of torques equals I alpha. And we have, I'm going to come back over here. We have torque due to the first weight plus torque due to the second weight plus torque due to the third weight. And let's put in our direction. Here's my axis of rotation. Remember, to figure out the direction of the torque graphically, I start at the direction head of the arrow, and I have to go around the axis. That torque is acting clockwise, and if we use counterclockwise as positive, if that's clockwise, that's going to be a negative torque. This one, it's going to get a little messy here, but I'll do it so that we can sort of see it. That's torque due to 2. That's going to be going in this direction. So that's counterclockwise. That will be a positive torque. And then same thing here. This would be a positive torque. It will tend to rotate. If this were the only torque acting about this axis of rotation, it would tend to rotate in that way. So we have to add up those 3 torques to equal I alpha. And as long as initial angular velocity is 0, they will add up to 0 Newton meters. And now I can ultimately see here, if I rearrange this, torque 1 plus torque 2 equals torque 3. So the torques on one side of the axis have to be equal to the torques on the other side of the axis. And so remember, each of these torques we figure out by FD perpendicular. We have the F's here, and we just need to figure out these D perpendiculars, and then we would have those torques. We would add those torques up, and as long as we put that fulcrum in the right spot, the torques tending to rotate in the clockwise direction need to add up to the torques acting in the counterclockwise direction. So it's just another way of looking at center of mass and what it represents, and center of gravity. And this really is, we're actually using center of gravity here because we're using forces and we're using weight. But in essence, these are the same thing as long as force of gravity is acting equally on these different masses. Okay, that is center of mass and center of gravity. I'll have some other videos to demonstrate experimentally how to determine the center of mass location, center of gravity location, and you'll have some labs on this as well. Okay, thank you.